All right, so the next thing we have to talk about is what's a computer. All right, so if you look up the dictionary definition of a computer, it says something like an electronic device for storing and processing data, typically in a binary form, according to instructions given to it in variable program. And to be honest, this is a really, really, really good definition of a computer. Why? First, there's a program involved that you can vary, like basically you can write a program in whatever shape or form. The program becomes an instruction to the computer, which is an electronic device. And the device store and process the data based on the program. And that's it. That's a really, really nice definition that kind of complete, to be honest. And with this definition, right, if you look deeper, logically, you have logic gates that handle computations. Logic gate means that you have an AND, an OR, and those like circuitry that you put together. For the purpose of this class, I assume that you know how to build add, multiply. If you do not know how to build an adder, multiplier, it's okay because we just assume that, hey, this thing exists and we can take it and use it. All right. But it's good if you know how to build them. Control signal. How do we control each component? And then the storage, which is how do I store data, right? Physically, you have things like transistor, capacitor, resistor, wire, and actually, to be honest, these days, a lot of new fancy materials outside of transistor as well to connect things together. But at the end of the day, it's a bunch of bits that somehow can mean something to a user, right? So a deeper look to visualize this, you have the processor with the control and the data path that talks to the memory. This is your DRAM. That's where you store the program and the data. When you're running any program, that program that you run is in the memory. Then you have the I/O, which store the binary file before you run a program, before you actually run it on your computer, is in the I/O in your disk. The I/O also represents things like network, keyboard, mouse, and anything that has the input/output to your processing and memory. Right. And then if you look back, right, the dawn of digital computing kind of start back in the day. It's been around for a long time. You have things like mechanical calculator, or even things like the Jacob's loom, which is shown in this picture, copied from Wikipedia. As you can see here, the right side, that looks like a punch card to you. It's actually a pattern that you can program. Now you can program, and this loom put together a bunch of threads, then weave the whole thing into a piece of clothing based on whatever pattern you want to program. All right. So quick fact, if you look at a lot of terminology we use in computer nowadays, threads definitely had a lot of influence from this particular machine. Over here, a program is basically the whole piece of cloth that you weave together at the end, right? When you're done. Then the program run a lot of threads, right? When you look at multi-threads, it's basically all this process together, and then you work through them to make sure they becomes a piece of clothing you can use afterward. All right. Then you have the ENIAC. The ENIAC is a machine that is considered kind of like the first electronic computer. It's all digital now. If you look at this, and if you look at the machine, right, you can see that these are all pluggable. You don't have moving mechanical parts. Anyone have watched the movie Imitation Game? The movie that kind of featured the life of Alan Turing back during the World War II era. If you have not, I do recommend you to watch that. But the machine, basically the premise of the movie is the German army has this machine called the Enigma machine that is capable of encoding the secret messages and broadcast that secret messages everywhere. So they can coordinate the attacks and the defensive position and whatever through the Enigma machine. And it turns out that to crack the machine, I mean, back in the day, the encryption mechanism is actually not that complicated. So if you can build a computer and kind of brute force to some initial condition that they can initialize in the beginning, you can uncover what's the secret message. So in the movie, there's a huge portion of the movie dedicated to how do I build this machine, right? And at the end of the day, when the machine is built, you'll see that it's a mechanical, there's a lot of moving parts in the movie. And in fact, the real machine also has a lot of moving parts. That machine is actually before the ENIAC. That was more mechanical machine that has a lot of moving components as well. It can be programmed, it can run a program. Right. The reason why the ENIAC has a lot of historical, I guess, being known more historically is, to be honest, it's kind of like the first time human actually have a machine that is driven by electronics. It can be programmed using these 3,000 switches, only have 20 decimal digit words. And you have the machine is huge. If you want to visit the real machine, it's in the University of Pennsylvania in Philadelphia. I did visit this is basically the picture I took. I think you can see the reflection of myself like on the mirror. I took this like in 2005 when I visited the university. If you look back in the 40s and 50s, there's a lot of hardware advances. You have the ABC machine by Atanasoff and Berry. You have C3 and C4, the SUSY machine by German. I think these machines are bombed during the war or something. I'm not sure. I need to double check that the fact. And then you have the Colossus and the Bombay. I believe the machine in the movie is the Bombay, but again, check the fact. I might be wrong. It might be the Colossus. And then you have the ENIAC, which is by Eckert and Moschly. And then afterward, von Neumann has the EDVAC, which then followed by Morris Wilkes' machine EDSAC. EDSAC also has another really important historical reasoning, which is this is the first time we have to store a program machine. You can store a program on the machine and run it. And then after you have the IS from Bigelow, and then afterward, there's the emergence of software. Because I guess after that point, scientists come together and it's like, hey, maybe you should to have a better centralized way to program the machine. That's when you have Fortran in 1954. So with the fact that you can now program in Fortran on a lot of machine, it helps with first machine building. Everything can be built optimized for program written in Fortran. Software building, I can then write a lot of program in Fortran and run on any machine, right? Afterward, you have the age of Moore's law. The age of Moore's law say that the number of transistors in the integrated circuit is going to double every 2 years. These slow down. To be honest, these has slowed down to every, I think, 3 years now. But you still have a lot of transistors that grow and grow and grow. A lot of people, to be honest, me included, would like to see where this is going to end. Because right now, we are at like 3 to 5 nanometer, right, for the transistor technology, 3 to 5 nanometer. How small can we get? Because at the end of the day, we are not going to hold a lot of electrons in the transistor. So there is going to be some end to this, right? So how are we going to handle the machine design when you approach the ends of Moore's law? It's a really, really big open question, right? So if you want to check out the paper, it's actually one of our reading lists for the first week. It's called Cramming More Components onto Integrated Circuits, 1965. Why do we want more transistor? To be honest, because the program always would like to have better performance. And when we change the hardware, we get more performance, right? So when you have the transistor, you have basically additional resources on your hardware that you can do whatever with that, right? You can do whatever with that. Anyone heard of this thing called cache? The CPU cache. The CPU cache acts like a internal memory next to the CPU. These are really fast memory, but it's a lot smaller than your DRAM. If you need to use something often, they can be stored in the cache, right? We can use transistor to build the cache. So if you have more transistor, you can build a bigger cache. Right? That's one obvious thing you can do. And there's many other things we can use when we have more transistor, right? Then you can do basically rinse and repeat. Have more transistor, build more things on your design, have more transistor, build more things on your design. Nowadays, we are kind of also approaching kind of the end of like how big your chip is gonna be. So there'll be a lot more interesting question, open-end question, including things like, do we want the chip to connect in a network-like manner so that we have a much bigger chiplet and they talk, right? Would that work? One of the reading is back in 2001 from Yale that looks into what would be the good opportunity on hardware research in 2001. Another recommended reading from Gabriel Low, this is kind of like a historical looking back. It's more like a retrospective paper. You might have noticed that the fastest computer right now is called the Frontier. This is a computer built by multiple companies, but the company that built the chip is AMD. Gabriel Low is actually kind of like one of the leader in architecting the chip for the Frontier computer, and he wrote the retrospective paper at ISCA 2023 on what happened on the design from year 2010, 2011, when the call for the chip for this machine are out from the Department of Energy. How did they design it? How did they change the component to make sure you can still get the the exaflops performance with some energy consumption restriction? So it's really power efficient, but it's also really fast. Now you can have a modern computer that looks like this, like Raspberry Pi, the GPU, even the supercomputer. And here's a picture from the Lawrence Livermore National Lab, which is one of the national lab in the US. The iPhone, really old picture. I think I forgot what generation. This is super old. All right, GoPro and quantum computer, right? These are all possible modern computers. Some of them are going to be used a lot more often. Some of them might not have a lot of practical use like now. For example, the quantum computer doesn't have a lot of practical use at the moment. But these are how we evolve, right? So we might discover new things. We might discover new applications. We might discover a faster way to solve problems through new hardware. Again, what happens when I run a program here? When you have a program as simple as like I just do one addition, 10 plus 20. You start from a program, go through the compiler, to the runtime, through the ISA, that becomes assembly, which then run the hardware, right? The question that you should then ask is, how can, for example, can I change the hardware to make this program run faster, right? How can I make it faster? One way you can think about this is, how do I even model my program when I want to run it? The first model is called the star program computer, or the von Neumann model. The name is gonna come up again. He's one of the prominent figure on computer, to be honest, on building computer, designing anything related to computer. There are two key properties. First, the program are stored in the memory array. So there'll be some memory, like DRAM, but you use nowadays, that store your program. That's where your program is located. And the memory is unified between instruction, or your program, and the data. So your instruction and the data are at the same at the same memory. So the control signal will just figure out, hey, whatever I'm reading or writing right now, is this your data, or is it a part of your instruction? The second really important component of von Neumann model is sequential instruction processing. Sequential instruction processing means that I run one line at a time and I run line by line by line. So if I start from line number 1, I then go to line number 2, then go to line number 3, then go to line number 4. This simplifies the hardware design a lot. Why? It simplifies the hardware because we can have this one counter that starts from line number 1, then we count up to go to line number 2, line number 3, line number 4, line number 5. We call this the program counter. This point to what line you are running right now. And it advances sequentially one by one by one by one, unless you have if, else, or for loop, which modify the program counter. This simplifies the hardware design because you can then always assume that the next line you need to run is here, then here, then here, then here, right? This assumption makes the hardware design a lot easier. So here's kind of like the illustration of things computer running in von Neumann. You have the inputs that can store your program in the memory, right? Your program is then processed by the ALU using your program counter. Once it's done, it's gonna put the data out into the output as a file or whatever, or it can be like a text on your screen. Then the control unit that has a program counter and register and everything kind of control where's your program, fetch, decode, and kind of like dealing with input and output, right? So the question you might have right now is, well, this is a model, it works, right? The question is, can I have a different model? Is there other model? The answer is this is not the only model. It's one of the most dominant because it makes sense. And it's actually really easy to program because whatever you want to do when you write a program, start from top to bottom. That's it, right? Haskell. How do you like Haskell? All right. Nong Bev, because you comment about Haskell, how do you like it? It's not that easy, right? To think about if I want to write a program in Haskell in this functional language, like where do I start? And how do I approach this compared to things like Python and C that start from line number 1 to line number 10, right? So the thing is, von Neumann is one of the most dominant because it starts from like the model is simple to reason, right? And our major instruction set architecture nowadays, including RISC-V, I didn't list the RISC-V architecture here. I forgot, sorry about that. But they use this model. So what's the alternative, right? The alternative that's really, really dominant in academia for a while was the data flow model. The data flow model do this in a control flow order. What does it mean? I would get the next instruction, whatever is available next. Things I can do, I'll do it right now. If I have to stop because the second instruction doesn't have the input yet, I can then go to instruction 3 or instruction 10. Data flow model compute when the operand, when the input to my operator is ready. So whenever I have all the inputs, I run. There's no instruction pointer. There's no instruction pointer. The ordering of your program is based on data flow dependence. Think of it as a math function. So let's say I'll go with one example here, right, in the next slide. In the von Neumann model, you have a program C equals A plus B, X equal B multiplied by 10, Y equal B plus X, C equals C plus Y. You run the first line, second line, third line, and fourth line. In the data flow model, I just do, hey, I need A and the first operator, the add, needs A and B. The second need B and 10. I have all of them, I can run them together. Then the multiply, have the results called X, which is used by the next ad, which is then used by the last ad, right? So as you can see here, the data flow model kind of expose that the first two operators can happen together in parallel. So as you can see here, the left side is more natural as a programmer. The right side is actually more performant. It's faster. So if you can somehow build a machine that looks like the right side, it's going to be faster. Data flow node can have many types, like the computation, relational, conditional, barrier. And we have one example here. I'm not going to go over this example this lecture. I'll do it in the beginning of the next lecture. But your homework as an extra credit is to tell me what does this do. So you have the slide from the course website. You can stare at this example a little bit and try to figure out what do they do. What is this logic? Right? And as you can see, you might then discover that something so simple can be complicated in the data flow model. So what's our solution as human? What we do to fix this, we want the performance from the data flow model. We want the simplicity of the von Neumann model or the sequential model. What we do is, well, let's fake data flow. Your CPU, not the GPU. GPU do a different technique. Your CPU that you use nowadays run the technique called out of order instruction. Out of order execution. That it fake this on von Neumann. It fake data flow. It basically run as if these are fake data flow program. But programmers still can do everything in von Neumann. So that's the CPU solution for you. That's why CPU is really, 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 really fast because it's doing this. Now, basically that kind of transition into the next topic I want to get into, which is ISA, right? ISA or assembly as we know it. So let's go from like C to assembly. How do you run a program? So let's say you have some program in C, right? The first thing you do is you would compile. Once you compile, you're going to have the binary, right? So once you have the binary, how do I run my program? Can someone answer this? How do I run my program? Come on, how do I run a program? How do you run your program? How do you open Microsoft Teams? This is how I can tell that everyone is tired by now. All right, so the way you run a program, you can double click on the icon. You can like run it on a shell. Basically, there's multiple ways you can run a program. But what happened is you have the OS, right? Runtime, which take your binary and then figure out what CPU should run this program. Then with this mapping, the other thing that the OS would do, the other thing the OS would do also make sure that this binary is copied over to your DRAM so that your CPU that has the program counter on this, so this is the program counter, can then point to the first line of your code. So that way, it's now your CPU know, okay, that's the first line of my code. That's the main function. I start from that line and go forward. OS copy the binary to the memory, and that's it. That's how you can run a program, right? So again, through the compiler, you can have this and understand everything, right? And here's a code example. Now, the code that you saw earlier in this lecture, right? Basically, it comes from this main function. Something really simple. A equals 0, B equals 5. I do A plus B. And to get the code, I can do obj-dump-s with the file name, with the object file. I'm going to get an assembly. And here, you see that it shows the main function, the name of the function that you're calling, the address of where in the virtual address, virtual address space, where is the code in DRAM. This is the actual binary. This is the actual binary of your code. And then here is the instruction that represent I want to add the two number and write the result into EX. And then here is the bits, the actual bits that represent the add instruction you saw, right? And that's assembly. Now, assembly is the part, well, basically it's kind of like, that's the ISA. What is ISA? ISA is something that allows us to talk to the computer without using ones and zero. All right. It only have electrical signal. So the only thing it can sense is on and off, on and off, on and off. So it's 1 and 0. Why binary format? Because we can represent the switch on and off easily. So then it means we can program with 1 and 0. So let's represent our human instruction. Something that we would like to instruct the computer to do in binary. So commands are in binary, data in binary. Data conversion of the data to binary is pretty simple. You should know it by now. I mean, how do I convert a decimal number to a binary? That's right. Command, not as clear. That's what the ISA is for. So we can use this as a way to interface between assembly code and a computer. And you can think of the ISA as it defines the list of the command that the computer can understand. ISA is a language. Let's say I compare this to English. If I say I understand English, because that's my ISA, it means that whatever is told to me in English language, I should know the meaning, right? So the ISA defines the list of commands that the hardware can understand. The microarchitecture is the implementation of the hardware, for that ISA, okay? Microarchitecture is the hardware that allows the circuit to perform those commands. So when you have the ISA, it has the list of commands. The microarchitecture is the implementation in circuit level. How do I have those commands? All right. And the microprocessor, as we know it, is the ISA plus microarchitecture. And this is the interface between your software and circuit. So the ISA will have things like instruction, add, subtract, multiply, branch, jump, load, store. So these include things like the opcode. What's the binary that tells these pattern? For example, the opcode can have something like if it's 1110000, this means we are doing an add. If it's 11001, this is a subtract. And we basically expand what pattern maps to what command. So that's the opcode. That's the verb. In English language, the opcode is the verb. It tells what do you have to do. It will have things like addressing mode. How do I go to the address in DRAM and the data type? It have things like instruction type. Is this computing? Is it loading something from the memory? Is it controlling where the program go next? It has the register and the condition code. Register, think of register as a small memory on your CPU. It's a temporary variable that you can use in assembly program. There are a few of them that you can use. If your program need more, then you have to use the memory, which is a lot slower. All right. Then you have the memory that has the address space. Where's my data and where's the data that the region of address that I don't belong here. I should not go and access those space. It should have addressability, which is How do we go and get to our data? Alignment. Do I do 4 bytes align? Do I do 1 byte align? How do I manage virtual memory? And for completeness, the ISA would dictate, okay, if someone hit something on your keyboard or move a mouse, when I have interrupts, when I have system call, how does it work? How do I handle access control or things like priority? The program with higher priority or lower priority, how do I handle that? How do I change the priority? How do I change something into a privilege mode? How do I handle I/O? How do I handle threat management? Or even things like how do I control power? There are designs that allow you to like throttle to make sure it consumes less power to save the battery. It used a lot in mobile phone. It used all the time, to be honest, on mobile phone. Things like thermal management. But if your CPU is running way too hot, how do I adjust the temperature? These are dictated in the ISA, and the programmer can use it. The microarchitecture basically is the implementation of these commands with some design trade-off. The microarchitecture is going to be transparent to the software. Whatever we do in the hardware should not be exposed to the programmer. Ideally, the way I program should not be dictated by how I design my hardware. I mean, it doesn't mean that you should not know hardware. It means if you know hardware and how it works, you can optimize your program. But as a day-to-day programmer, I don't want you to worry about what are the optimization I do in the hardware, because I do not want to make your life more complicated, right? So these are different techniques that are done all in hardware that make your CPU faster without you noticing. Even things like error correction. What if there's a bit flip in your DRAM? How do I detect that and flip it back, right? And there are trade-offs. For example, floating point 32, which is the standard IEEE floating point 32-bit format. NVIDIA came up with TF32, TensorFloat 32, which is basically, it doesn't use 32-bit. There are trade-offs with that, right? So it covers the same range, but you cannot, your result, your number is not going to be as accurate. So you're more efficient in terms of performance. You're sacrificing the accuracy for your multiply. Number of register. If you have more register, you have more control over what can I use as a temp value in my CPU. But then you're sacrificing the actual transistor to implement those register on the chip. Okay. Number of ports. How many parallel read and write into the register? These cost more hardware. Or even things like if I want to do one multiply, how long does it take? Right? These also dictate how fast your CPU is going to be, how complicated your CPU is going to be, how much power your CPU is going to consume, right? And if the ISA changes, so if the ISA changes, what happens is your computer no longer understands the new ISA. It's like suddenly everyone speaks French. I'll be like, I don't speak French. I don't understand what you're trying to tell me to do, right? So that's what happened when ISA changes. Program without source code will stop working. Program with source code will have to be re-optimized using a new compiler. Another alternate solution is translator. This is code transformation. So if you use the M1 chip from Apple, you might have noticed that program compile for x86, program design for x86 can run on Apple M1 or M2 through a software called Rosetta. That's the translator. Basically, it translates x86 assembly into ARM assembly and run on MacBook, right? But the conclusion is you don't want a lot of ISA. And so that's why you don't see a lot of assembly language compared to programming language. You see a lot of programming languages, but you see only a subset of assembly languages that are now around in the world, because you want to make sure you build a compiler for that ISA, and it's kind of a pain to change the ISA all the time, right? And here are some trade-offs. For example, you can have the different complexity for instruction, how they are specified, and how do I support different features in my ISA. Can I support low power mode? Can I support the mode that doesn't use a lot of memory. Can I support SIMD, which is what the GPU, one of the core thing in GPU, right? Can I support vector instruction? Do I want to have the complex ISA versus reduced ISA? All right, so we'll wrap up this lecture with this slide. Complex ISA versus reduced ISA discussion. CISC versus RISC. So next week we'll come back, we'll resume and kind of briefly talk about what's the trade-off and how do we logically kind of figure out what is the benefit of circuit design and how do we get the best of both worlds and what are the different things that different flavor of the ISA from RISC-V to 886 to not sure if I have the ARM example, but you can see it from the manual as well. All right. So that's it for today's lecture. I would like to kind of wrap up before noon. So now it's 11:50. I'll stop the recording. We'll use the rest the rest of the class here for any Q&A because everyone seems tired right now. All right. Thank you so much for being here. If you have any questions, feel free to ask me. It can be in Thai, it can be in English. Either way works. I'll be here until noon. All right. Thank you so much.